Hi everybody, and welcome to Theorem 9.3 on page 71 of the workbook. Let's take a minute to read this theorem together. Okay, so this is telling us that G is a group and Z of G is the center of the group, and if we know that G mod Z of G is cyclic, then G is abelian. Okay, now let's remind ourselves what some of this notation means here. Okay, so the center of a group is the set of all elements that commute with everything in the group. Okay, and earlier in the course we've talked about how this actually forms a subgroup, okay, and in fact a normal subgroup of the group G. Okay, so this theorem we're basically trying to show that if we know that the factor group G mod the center is cyclic, then that's enough to allow us to conclude that the overall group is abelian. Okay, we're going to see if we can prove that. Okay, and just to warn you, this is one of those proofs where there are a couple of lines where we make a few leaps. So there are some steps in this argument that maybe leave it to you, the reader, to think about, okay, and to fill in some of the little gaps that we're going to make, okay, or little jumps that we're going to make. So let's start out with our assumption here. So this is an if-then statement. We are assuming that G mod Z of G is cyclic. Okay, so we'll take that as our if. And so since we're assuming that that's cyclic, that just means that this factor group can be generated by one element. There's got to be a generator. Okay, one way of saying that is there's got to be a G in our group G such that if we look at all of the powers of the coset, G times Z of G, we're going to have to get our entire factor group. Okay, now this notation might look a little bit intimidating, but this really is just the definition of a cyclic group. It's just saying that there's got to be a generator that generates everything in our factor group. In this case, we're giving that generator the name G times Z of G. That's the coset that's generating this factor group. And this is an equation that we're going to be coming back to, so I'm going to give that a name. We'll call it star. And let's think about where we're trying to go here. What are we trying to show? Okay, well, we just assumed the if part. We're trying to prove that G is abelian, and that just means that our group operation is commutative. So we're trying to show that AB equals BA for every A and B in G. That's where we're hoping to get here. All right, well, let's start by just choosing any two elements that are in G. Okay, and here's how we're going to get started. We're going to start by thinking about the cosets that are generated by these two elements, A and B. Okay, so one coset would look like A times Z of G, and the other would look like B times Z of G. Well, the thing is, both of those two cosets are in the factor group, G mod Z of G, and because it's a cyclic group, that means that both of these two cosets have to be generated by this element. If we take the right power of our generator, we should be able to get those two cosets. Okay, so let's see if we can put that observation into words. Okay, so by star, there exists an I and a J and Z, just integers, powers, such that the coset A times Z of G is the ith power of our generator, and the coset B Z of G is the jth power. Okay, we're just saying we know that those powers have to exist because our factor group is cyclic. Okay, and then we remind ourselves what that means. If we take the coset G Z of G and raise it to the ith power, by definition, that's just G to the I times Z of G. Okay, similar statement is true down here. Okay, so we've got those two statements. All right, and now here's going to come the first statement that might be a little bit of a leap here. I'm going to go ahead and just state this, and then we'll try to make sense out of it. So I claim that as a result of that, we know that A, the element A, has to be expressible as g to the I times x, and B has to be expressible as g to the j times y for some x and y in z of g, the center. Okay, now where in the world does that statement come from? Okay, that seems like a pretty big leap. Okay, well, let's look at those one at a time, starting with the element A here. Okay, notice that A has to be an element of this coset for sure, okay, because one of the elements that we know is in the center is the identity element. Okay, and if you take A and multiply by the identity element, you're going to get A. And so since A is in this coset over here, it's got to be in this coset because those two things are equal, which means that A has to look like g to the I times something that's in z of g. That's exactly what we said in this statement here. Okay, and then we can say a similar thing for B. Okay, B has to live in this coset, and that coset is equal to g to the j times z of g, so that just means that B has to be expressible as g to the j times some y that lives in the center. Okay. All right, now let's see what we can do with that observation that we made. Okay, so as a result of that, here's what we claim. If we start with AB, that's equal then to g to the I x times g to the j y, just using the representations that we made. And now we're going to use the fact that x is in the center of g. Okay, up here. What does it mean to be in the center again? It just means that it commutes with everything in our group. And that means then that we can take this x and we can move it around. We can move it all the way to the end if we want to, because it commutes with every element in our group. So this is equal to g to the I times g to the j times yx. Okay, that's an important step, so I'm going to remind you of the reason there. All right, and then this is equal to that. All I did there was reverse the order of the g to the I and the g to the j. That's actually a property that's true in any group. You might remember talking about that way back near the beginning of the course. Okay, and then I claim that this is equal to g to the j y times g to the I x. Where does that come from? Okay, well, what we did there was we took this y and we just moved it over here. How can we get away with just moving that y around? Well, that again comes back to the fact that y is also an element of the center of G. Okay, so we can take y and switch its order with anything that we want to. But look at what we have now. G to the jy times g to the ix, that's exactly equal to b times a. And if you look at where we started and where we stopped, we started with AB and we showed that it's equal to BA. That's the definition of what it means for G to be abelian. Okay, and we're done with the proof.